This is probably the last video for reciprocal frame vectors that we're going to do. I'm going to go through the gradient representation of the reciprocal frame vectors, where we'll find that our reciprocal frame vectors are the gradient of our parameters. We're going to find that the representation of the gradient is a mixed indexed expression, and it has curvilinear representation in terms of the parameters as follows. We're going to also show that we've come up with this result indirectly for the m equals 2 case, where we had an n-dimensional vector space and a two-dimension manifold. And we're going to show that in the m equals n case, where we have an n-dimensional n parameters, then that reduces to the following representation, and that this is the representation that's equivalent to the gradient representation of the reciprocal frame vectors. We're going to define the derivative in terms of the directional derivative. So recall that a directional derivative has the following form. It is the limit, let's say as some parameter goes to 0, it's a directional derivative of f, and f can be a multi-vector function. So we say f of x plus at minus f of x all over t. So a more compact way of writing this is the derivative of x plus at, and x and a are vectors, with respect to t, all evaluated at t equals 0. This is an implicit definition of the gradient and gives us this required structure of the gradient, especially for non-Euclidean vector spaces, where we're used to defining the gradient in Euclidean vector spaces as the sum of ei over d dxi. We'll see that we need to tweak that slightly for non-Euclidean spaces and for curvilinear coordinates, and for non-Euclidean spaces we need upper index here, which can then also be sometimes written as ei di, where di is d dxi. So a dot grad of f. So if we evaluate this derivative, we have this f is a function of x1, x2 to xn, and so df dt by chain rule is df, this is of x plus at, so xi plus ai d xi plus at ait, that's just a scalar derivative times the differential of dxi d ai d dt. And we're going to evaluate this at t equals 0. So that is t equals 0. This is df dxi times ai. So we have a structure that here. So a dot grad of f is ai df dxi. So we can tidy this up slightly by introducing a factor of 1, a common trick. So let's say ai times ei times e upper I df dxi. This is the sum over i's, and here we're making use of the fact that ei times ei equals 1, because they're reciprocals. So given that, we can now factor this out as a dot product of A dotted with EI, sorry for the mess, EI d dxi applied to F. This shows us that the representation of the gradient is E upper I d dxi, where EI dotted with EJ is delta ij. This is a general representation of the gradient for non-Euclidean spaces. And we want to see we also want to find out the representation of the gradient in terms of curvilinear bases for Euclidean or non-Euclidean spaces. Let's do that next. So if we have a parameterized space where x is a function of a1, a2, and so forth, then it is EI df dxi in terms of all the a's. Chain rule. Again, it gives us the answer. That is EI times df daj, say, daj dxi. And we can group our I indices. So that's EI times d dx I of a j times df daj. And what do you know? We have a gradient in the first factor. So that is the gradient of aj all times df daj. What we want to now show, and this is a theorem, is that xj, the reciprocal vector, equals the gradient of aj. So if we do that, then we find that the gradient is xj d daj. So this is a consequence of the theorem once we prove that theorem. So let's prove that theorem. So we want to show that xi is reciprocal to xj, which is d dx daj. Let's write this out. So xi dotted with xj is ei d a. Don't need different indexes. Say I prime d dx I prime dotted with dx daj, which is say k dx k daj. And taking our dot products, we have a delta I prime k times dai dx I prime dx k daj. And there's an implicit sum here over all the repeated indices, and we are left with, let's place the I prime by k, so we have dai dx k dx k daj, which is just a chain rule expansion of dAi, dAj, and sure enough, that is delta ij. So we have just proved that x upper I dotted with x lower j is delta ij, where x upper I is the gradient of the ith parameter. Given a gradient representation of our reciprocal frame vectors and a corresponding parameterization of our position vector, it's not exactly obvious how you go about computing such gradients. It's a little bit tricky because we need the parameters to be defined in terms of the position vector coordinates, and so we can use an example to illustrate how one strategy for computing these in general. So let's start with a circular parameterization. So if we have a radius and an angle, then we could say that x equals r cos theta and y equals r sine theta. And so we could actually, this parameterization in this particular case is simple enough that we can actually solve for, r is x squared plus y squared, and we can solve for theta. Let's say theta is, the tan theta is going to be sine over cos, which is y over x. So here's a solution for r. We can make a full solution should we want to. X squared plus y squared, and theta is the arctan of y over x. But we can actually work with this implicit form just as easily. So if we wanted the gradient now of r, for example, so that is E1 dr dx plus E2 dr dy. And we don't have dr dx, but we can say what is, let's look at the gradient of r squared. That one is easy to compute. That is just going to be E1 times the gradient of dx squared dx, which is 2x, plus E2 times 2y, and gradient of r squared is going to be r grad r. So now we have grad r is E1 x over r plus E2 y over r, and that is x over r is cos theta, and y over r sine theta. So we're left with E1 e to the I theta. So there's grad r. That wasn't too hard, and that sure enough is our r hat unit vector. Now how about grad theta? So let us compute. So we want grad theta. So let's try grad of tan theta, which is, that is sec squared theta grad theta, and in coordinates we have equals grad of y over x So grad of y over x is E2 times 1 over x plus E1 minus y over x squared. So we have 1 over cos squared theta grad theta. So you see when you do implicit differentiation, so we have cos squared theta times and is this all right? X is times e2 over x. X is r cos theta minus e1. Y is sine theta over r cos squared theta. So y is r sine theta, and x squared is x squared cos squared theta. And I just canceled out one of the r's. So we're left with 1 over r all times e2 cos theta minus e1 sine theta. And that's what we expect. We can just finish writing this out. That is 1 over r e2 cos theta minus e2 e1 sine theta 1 over r e2 e to the I theta. And that's what we expect. We could have considerably more complex parameterizations. Imagine we have x is f of r theta, y is g of r theta, and f of g are sort of arbitrary functions and non-separable, unlike the circular parameterization that we had. How do we go about and compute the gradients in this case? So specifically, let's say we have a number of coordinates, and each of these coordinates is a function of each of our parameters. So we want to compute the reciprocal frame vectors as the gradients of each of these parameters. We can compute the gradient of this side of the equation pretty easily. So we say grad of xi, which is just e j ej dxi dxj, which is just ei. So there's the gradients of our coordinates. And now we want to use chain rule to evaluate the other side. So if we have grad xi, we can say that is e j dx I dxj, e j d dx I d a k d a k dxj, which is ej ddak dxj, just grouping terms, and dxi dak. Grad ak times dxi dak. So we see that, and that is ei. So we see that we can solve for the gradients, but that means that we have to solve this linear system. Each of the gradients is then dependent on each of the others, and all of the derivatives are coordinates with respect to our parameters. So let's try to put this into a matrix form. So first we note that this is our xk times dxi dak. Not matrix form yet, but we have a sum of AKs. So we can write this as x1, x2 to the xn. These are the reciprocal frame vectors, not the coordinates. And then we have dxi, dA1, all the way down to dxi, dAn. All right, so, and this is EI. So we've got the right side of this equation in matrix form, and the left side is not yet. So this is a vector, and we have matrix times a row column vector, and we could then form, E1, E2 to En, which will just be an n by n matrix, equals, and let's call this part X, and we have here dx1, dA1, down to dx1, dAn, all the way over to dx n, dA1, dx n, dA1. Now, each of these, we have dx1, dA1. So if I come across here, we have all the derivatives of the coordinates with respect to A1, and as we go down the rows, the derivatives with respect to AN. This should be N. So X times dx dA1 transposed down to dx dAn transposed which is, so we have E1 to En equals X. That is vector X1 transposed down to X N transposed. This matrix here is our Jacobian matrix. And you see the determinant of the Jacobian matrix written as dx dx1, dx2, dx n. So when you take the determinant, the transpose doesn't matter. And anyways, that's our Jacobian matrix. So we have a system here. We want to solve for all of our reciprocal frame vectors, and we are multiplying by all of the set of our curvilinear vectors for the tangent space, and then we have this strange beastie on the other side of all of our standard basis reciprocals. So let's see what we can do with this guy. We know that if we take, let's say we take EI dotted with EJ, that is delta by J. We can write that in matrix form as EI G, EI transposed G E EJ. And if we put this as matrix, we have identity. And so we have E1 transposed down to En transposed as matrix factor, then G, then E1 to En. Equals I. This is also equal to I. So we're left with G E1 to En equals I. So our matrix of the standard basis reciprocals is just G inverse. So we're now left with G inverse equals X J. So X is G inverse J inverse or J G inverse. Given an arbitrary parameterization, we can assume that each of the xi's, so x1, x2, down to xm for an m parameter manifold, have the form of alpha 1 So we can assume that we have some system of equations that represents our reciprocal frames. And we can now put this into matrix form. So we can say that x1 to xm, all of our reciprocal frame vectors equal J transposed alpha 1 to alpha m. And J transposed here is x1 down to xm, because we wrote that J was x1 transposed down to xm transposed. Our matrix of reciprocal vectors equals J transposed times these coefficients to be determined. We also know that we should have JGX equals I. So this is all of the dot products of xi dotted with xj put into matrix form. So now we can multiply here on both sides by jg. So we have jgx equals jg J transposed alpha 1 to alpha m, and this is now identity, and we now have an invertible matrix that we've now squared our matrix. So we are left with alpha 1 down to alpha m equals J transposed inverse. We can go and plug that back in for x, and we know we found that x is J transpose times J transposed inverse. There is the general form of our reciprocal frame vectors in terms of the matrix algebra, in terms of the matrix, the Jacobian matrix and the metric matrix G. So it looks a little bit different than what we found when we evaluated the gradients. So with gradients, this was the M parameter manifold. And then where M equals N, we found that X was JG inverse. So these should actually be the same. This is equivalent to our geometric algebra representation, where we found that x1, for example, was x2 wedged with xm, all dotted with 1 over Jx1, Jxm. So if we were to write out our geometric algebra solution in terms of matrices, we'd get this. And when we calculated the reciprocal vectors by using the gradients, this is what we found. So this was our method of computing those gradients, which required solving a linear system. And so the key here is that in the case that m equals n, then our Jacobian matrices are square and invertible. And so if that is true, then we have x equals J transposed. I'm just going to write it out once more. J transpose inverse, and we can go and do these inverses now term by term. So J transposed inverse G inverse G and J inverse. And we're left with G inverse J inverse, which is just J G inverse.